Okay. Hi, everyone. Today, our group is going to talk about wastewater treatment system, and in particular, the optimal time for adoption of wastewater treatment facilities. The group members today are Jennifer, Jackie, Nolan, Pepe, and Yin Ting. Next slide. So let's dive into our problem. Next slide. So our question is, what is the optimal time for a specific city to transition from a decentralized septic system to a centralized wastewater treatment facility? Now, a septic system is mostly found in rural areas of states. They're essentially a large tank that's hooked up to one household. On the other side, we have a wastewater treatment facility, and this is a large facility that's typically hooked up to various houses through pipes, and it takes back the wastewater and recycles it for reuse. The tools we use today is cost-benefit analysis, sensitivity analysis, and optimization. Next slide. So now let's talk about our methodologies. Next slide. So for our project, we broke down our analysis into two stages, sorry. In our first stage, we do our optimization problem, and we try to identify the optimal time to transition to a wastewater treatment facility. In our second stage, we do a cost-benefit analysis where we compare our first scenario of adopting a wastewater treatment facility to a second scenario where we stay on septic systems. Next slide. Now, for our analysis, we found data that's mostly from Oregon, and we developed new variables using regressions. We also use outside sources to find our parameters and develop equations for our analysis. Next slide. Now, using this data, we were able to predict population, in particular housing density. We were also able to find other important factors to our analysis, which include the city budget, costs such as pipe costs and machine costs. And we use this data essentially to find the optimal time for a transition that minimizes our capital expenditure costs with respect to the budget given in the context. Next slide.
So I'm going to talk a little bit about what are our outcomes. So these are our quantitative outcomes. So these are going to get a little bit mathy. So our first quantitative outcome is our optimization problem. So on the screen, what you can see on the x-axis is the population of any given city, or of our generic city. And then on the y-axis, you can see the ratio of wastewater treatment capex to city budget. So we want to minimize this, right? Get that y-axis as low as possible. Now, we have the most confidence in this blue estimation line, which is our pipe cost estimation, which we pull from North Carolina. So we want to follow that down. That line gets asymptotic around 3.4. So essentially the ratio of the total cost of a wastewater treatment system is 3.4 times as much as an annual city budget. So what we want to look at is where does this cost sort of start to really achieve most of its savings, and then things start to plane out. So we want to zoom in really close on this 5,000 to 10,000 population range, because that seems to be sort of an optimal area for construction. So we wanted to do a little sensitivity analysis and figure out how sensitive these numbers were to changes in our assumptions. So two key assumptions we had were the dollar exchange rate and the uptake rate. What we found was that as you vary the dollar exchange rate, the overall cost, the optimal population for investment stays roughly the same, right? So that's why you see flat lines. The dollar exchange rate played into a couple of our costing models, and so that was why it was a variable of interest and high uncertainty. Our uptake rate. The uptake rate is the rate at which citizens or households in a city adopt wastewater treatment sort of centrally when it's introduced, right? So we have the construction of the plant, and then maybe 50%, right, half the people want to hook up to the system initially, or maybe 100% want to hook up to the system. And so what we see as we vary that uptake rate is that the optimal population range sort of tightens and comes way down low, right? So our base assumption was about 80%. So you can see that gives us our output of between 5,000 and 10,000, which is sort of what we think is about accurate. As you get higher in your uptake rate, then the optimal population comes down. So we want to talk about two different things, two different types of costs for our cost-benefit analysis. One is private costs and one is community costs. So private costs are costs from the perspective of the individual, right? So we pay bills to essentially have our water treated once a wastewater treatment plant gets built, and that feels to me like a bill, right, like a cost. In contrast to the city, my bill feels like a benefit or an offset to construction costs. So you get these two radically different perspectives, right, from the town and from the individual. So here, we're looking at two different policy alternatives, the wastewater treatment plant construction on the left and reliance on septic on the right. We also look at community and private costs, and then we look at our base case where we're at 5,000 people and late adoption and early adoption. Key things to note here are that private costs, which are unbolded, are always more than community costs, which are bolded. That's because people have to pay bills all of a sudden they used to not have to pay. We also wanted to do some sensitivity analysis with this, so we varied a couple of things, including the annual population growth and the starting population. So essentially, that's the late and early adoption. So when we vary annual population growth, we essentially see that costs balloon, and costs particularly balloon from the perspective of the private citizen. The same happens with the starting population, right? So early or late adoption. So what we see is essentially that private citizen costs are super sensitive to variable changes, while community costs are not so sensitive, meaning that sort of private people may be justified in some of their reticence to join systems like this. What is our answer, right? What is our policy recommendation? What is our outcome we are interested in? So our main thing is the cost to budget minimization, right? That ratio minimization follows an asymptotic decline to about 2.4. But we don't want to wait until it hits 2.4 because that takes a long time. Instead, what we want to do is invest early enough that cities can sort of reap the benefits of increased commercialization, things like that. And so our real recommendation comes out to be that cities with populations of between 5,000 and 10,000 seem to be sort of in the Goldilocks zone of wastewater treatment plant construction from an optimal budgeting perspective. From the community and private cost, right, the cost benefit perspective, things are a little murkier, right? Because those private costs are super high compared to the community costs. And so there's going to be a lot of people, and there are a lot of people in cities that transition who don't really want to transition. And so that's going to be a big political hurdle to overcome. Now I'm going to talk a little bit about some of our limitations and some further research we're doing. So our limitations here, one of our major limitations is we only look at the initial construction of one wastewater treatment plant. We don't look at expansion. We don't look at sort of, long-term development of the city. Also, we look at a random city, right? This is a generic city, and so we don't account for much heterogeneity. Our environmental quantification is also sort of lacking because there is a lack of data and because we are really interested in sort of the dollar impacts on individuals. We plan to expand some of our baseline characterization and get some more detailed parameters and inputs, and we're collaborating with a lab out of Oregon State University to do that throughout the coming months, I think. So yeah, thank you so much, and yeah, enjoy class.